Imaginary numbers are one of the most fascinating concepts in mathematics, extending our number system beyond what we can physically count or measure. Consider this intriguing equation: x squared equals negative 1. At first glance, it might seem like a simple problem to solve, but there's a fundamental challenge here. What number, when multiplied by itself, gives us negative 1? If we think about the numbers we're familiar with, this seems impossible. To understand why, let's examine what happens when we square different types of numbers. When we square a positive number like 3, we get 9, because 3 times 3 equals 9. What about negative numbers? When we square negative 3, we also get positive 9. This is because negative 3 times negative 3 equals positive 9, following the rule that a negative times a negative gives a positive. The same pattern holds for any real number. 5 squared is 25, and negative 5 squared is also 25. No matter what real number we choose, positive or negative, its square will always be positive or 0. This reveals a fundamental property. Any real number squared is always greater than or equal to 0. It can never be negative. This creates a dilemma for our equation x squared equals negative 1. Within the realm of real numbers, this equation simply has no solution. We've reached a limitation of our number system. To overcome this limitation, mathematicians took a bold step. They invented a new number called I, defined as the square root of negative 1. This wasn't just a notation trick. It was an expansion of our entire number system. By definition, when we square I, we get negative 1. This is what makes I different from any real number. It's the only number that, when squared, gives us negative 1. It exists outside our real number line. And just like that, our original equation x squared equals negative 1 now has a solution: x equals I. We've solved a previously unsolvable equation by expanding our concept of what numbers can be. With the imaginary unit I, we can now express the square roots of any negative number in a consistent way. This opens up a whole new family of numbers called imaginary numbers. For instance, the square root of negative 4 equals 2i, because 2i squared equals negative 4. Similarly, the square root of negative 9 is 3i, the square root of negative 16 is 4i, and the square root of negative 25 is 5i. In each case, we're finding the positive number that, when multiplied by I, gives us the square root of a negative number. Imaginary numbers fundamentally expand our mathematical toolkit. They allow